Okay, so we're going to wrap up, I think, the rest of chapter 6, maybe. We're talking about types of reactions. And before we talked about really two categories of reactions. Again, double displacement reactions, which are your kind of two ionic compounds. Where once again, the positive guys basically will switch partners and we will get some new ionic compounds on the other side here. And once again, sort of double displacement is like the big sort of classification of types of reactions, and really more specific ways to classify some of these double displacement reactions are as precipitation reactions. And that obviously is when one of these guys make a solid, and also really acid-base reactions really fall under sort of the double displacement umbrella. And really that's when one of these guys will be water that's being formed, a result of the H plus from the acid, the OH minus from the base. And pretty much all other reactions, which is where we're currently at here talking about, fall under the redox umbrella. And the redox reactions means oxidation and reduction reactions. And really this involves transfer of electrons. And when we have a redox reaction, we have an oxidation that can occur. And oxidation means that we lose electrons. By the way, there's a few other definitions of oxidation, like we gain oxygen from reactants to products. We also can lose hydrogen as you go from reactants to products. So these are two other sort of definitions of oxidation and reduction, which always occurs together. So if somebody is being oxidized, or again, somebody's being reduced, they do occur together. So you would expect the opposite to occur there. And a reduction, it is the gaining of electrons. They also have these similar type of definitions as well, when we lose oxygen from reactants to products, and when we gain hydrogen from reactants to products. Those are a couple other definitions of reduction as well. I would say in general chemistry, we pretty much focus in on the losing and the gaining of electrons. If you continue on and take something like organic chemistry, you deal a lot with gaining and losing oxygen or hydrogen in terms of reduction and oxidation. Again, in organic chemistry, it's pretty much like all nonmetals, so it's a lot easier to kind of follow the gaining or losing of hydrogen and oxygen as it is here in general chemistry. A reminder as well, we also talked about the idea of the reducing agent, which again is different than the thing going through reduction. The reducing agent is the substance that is oxidized, and the oxidizing agent is the substance that is reduced. And as we talked about last time, pretty much they're called that because they cause that effect in the other substance. So the reducing agent, in order for it to cause the reduction in somebody else, it will lose electrons, so it gets oxidized. The oxidizing agent, in order to cause somebody to be oxidized, means it needs to gain electrons, so it's got to take those electrons. So again, oxidizing agent, reducing agent, a different question than what is being oxidized and what is being reduced. So you do want to keep those things straight. How can you figure out what is happening, oxidation or reduction? You know, you can just do a very simple number line, as we talked about. Positive, negative numbers. When you lose electrons, you become more positive. So if you see yourself on the number line sort of moving in that direction to the right, that substance is going through oxidation. And when you gain electrons, which is what happens with reduction, you should be becoming more negative. So if you see yourself sort of moving on the number line in the negative direction, that guy is going through reduction. Now, under the redox umbrella, which we'll talk about here in just a second, falls pretty much all other types of reactions. And through both of those sort of big classifications, we do take care of pretty much why all reactions take place: the formation of a solid, the formation of water, and really the transfer of electrons is really, again, the three main reasons why some type of chemical reaction takes place. We talked about that you can write half reactions for redox reactions. And when we write half reactions, we have something like this. A half reaction such as this, electrons are on the product side. That is an oxidation half reaction, where you have the electrons on the product side. And that's different than, say, a reduction half reaction, where you have something like this. That is where we see the electrons on the reactant side. It is a reduction half reaction, like it is being gained. They're called half reactions because, frankly, when you add them together, you get the overall reaction that is taking place in that particular situation. One really important thing, especially when you're balancing sort of redox reactions, these sort of simple ones, we'll talk about complex ones probably tomorrow. But when you're balancing these sort of simple half reactions, you always want to make sure that the electrons in both half reactions are the exact same number. And that may require you to multiply a half reaction by a number, or maybe multiply both half reactions by a number to get the number of electrons the same. So for example, if this was, say, 2 electrons here, and we wanted to add this together, we would then need to multiply the top guy by 2, and it would distribute that 2 all the way across here. And now we could add these together where everybody on the left-hand side stays on the left, everybody on the right stays on the right, and anything on opposite sides will cancel. So I'll get rid of that since we distribute it. So those guys would cancel, and it would give us our overall reaction here that looks something like this. And mine. So in the basic redox reactions, half reactions, we got to make sure that they are the same number of electrons. And the reason for that is it happens together. So however many electrons that somebody loses should be the exact same amount of electrons that somebody gains. So it's sort of a perfect transfer of electrons from one source to the next. And we could add our half reactions together. Any questions on any of that stuff we talked about last time? We also saw that you could write sort of a net ionic equation as well for sort of a redox sort of reaction as well. You will typically have probably just like maybe one spectator ion that's sort of happening. All right. So how can we determine sort of what is being oxidized, what is being reduced? We really do look at what is sometimes referred to as the oxidation number. It's also sometimes referred to as the oxidation state. And the oxidation number or state is the charge the atom would have in a molecule or an ionic compound if the electrons were completely transferred. Now, when we talk about oxidation numbers or oxidation states, they are different than a lot of people have in their head when we talk about ionic compounds. So in ionic compounds, like we talked about with naming and stuff like that, you know, hey, chlorine is -1, you know, oxygen is -2, you know, all those kind of things. Nitrogen is -3 and things like that. And they will remain those sort of oxidation states in an ionic compound. But when we're talking about sort of covalent bonding, nonmetals and nonmetals, and sharing of electrons, some of the elements do take on a different oxidation state, and it's different than we kind of have in our head and when we think about sort of nomenclature and typical charges that occur. So let's talk about the rules of assigning oxidation number, and this will also help you obviously determine, you know, what is being oxidized and what is being reduced. The first one is pretty simple. Any element that's pretty much uncombined, it's by itself, it's how it's found in its natural state, will have an oxidation number of 0. So anything like sodium metal by itself has an oxidation state of 0. Hydrogen, oxygen, nitrogen, those guys all have oxidation states of 0. In a monoatomic ion, the oxidation number is equal to the charge. So if you're dealing with something like lithium, it will be +1 will be the oxidation number or state for it. If you're dealing with an iron 3 ion, it will be +3. Oxygen, which is really a great place to start in a lot of cases in terms of assigning oxidation numbers, will typically have an oxidation state of -2. The one place where oxygen will not have an oxidation state of -2 is actually when it is not really oxygen, it is peroxide, which is this guy right here. It is actually a polyatomic ion, and it will have a oxidation state of -1. So in hydrogen peroxide, the oxygen here is actually carrying a -1 charge, and that's why there's two of them to balance out, obviously, the +1 charge that we have over here. I would say you would typically know it's peroxide. It's usually hydrogen peroxide. There's sort of an extra 2 in there a lot of times with the oxygen, as opposed to oxygen. Probably 9 times out of 10, it's probably safe. If you see oxygen, it's going to be a -2. But again, there is that occasion where it could actually be peroxide and it could be -1 that's happening. Now, when we have something like hydrogen, it is going to be +1. The only exception would be when it's really in the hydride form, and that would be if it comes after a metal. So like LiH, the H there would be -1. Group 1 will always be +1. Group 2 will always be +2. And fluorine will always be -1. When we add up all the oxidation numbers together, it does need to equal the overall charge that the substance has. So if it's a neutral substance, everybody in terms of their oxidation states need to equal 0. If it happens to be an ion or something like that, like a polyatomic ion or maybe or something of that nature, and it has an overall charge of -1, then when you add up all your oxidation numbers, it does need to equal -1. Oxidation numbers do not have to be whole numbers. For example, there you could have like -0.5 when you do that. When you do assign oxidation numbers, you should also always assign the charges. So if it's +1, you should write +1. If it's -1, you should write -1. So you should include the pluses and the minuses when you're assigning oxidation numbers. So if we look at something like this, which is bicarbonate here, HCO3-. In a situation where you want to assign oxidation numbers, especially in a situation where you got 3 things, usually you kind of save the guy in the middle for the end. So if you have oxygen, that's again a really good place to start. We would start with oxygen, which would be -2 in this case. The 3 oxygens there give us really a grand total of -6 sort of happening over there. The hydrogen going to the left-hand side is +1, again, leaving the guy in the center for the end. That gives us basically +1 and a -6, and it does have an overall charge of -1, which means that needs to equal -1, which means in this particular case, the carbon here is taking on a +4 sort of oxidation state in this particular situation. So hydrogen here would have an oxidation state of +1. Carbon here would have an oxidation state of +4. And oxygen here would have an oxidation state of -2. So another very common mistake that people make is they go, oh, well, there's 3 of them, so it's a -6 oxidation state. And that is not the correct way to indicate the oxidation number. So if you're asked what is the oxidation state or number for oxygen in a situation like this, it's basically just one of them by itself. So it would be -2 is the correct way to basically display that. Again, you can see they all have the charges also written with it, so make sure that you do include the charges as well. Any questions on that? Okay, so let's take a look here at a chart. Here's some different oxidation numbers, and like I said, there's a lot of different oxidation numbers for things. And again, we're usually used to things, for example, again, like nitrogen, being, for example, -3 in an ionic situation, but it can be like +5 and things of that nature. Chlorine and bromine, we're used to it being like -1, but it could be a lot of different oxidation states. And again, this happens because these guys are not in an ionic compound where they have the electrons have been completely transferred to them. They're basically sharing electrons in a covalent bonding situation. So this is sort of the charge that they basically take in that situation. So for each of these, let's take a couple minutes here and let's identify the oxidation numbers for each of the elements that are here. So take a minute or two, see what you come up with. Okay, let's take a look, see how we're doing. So once again, I recommend if you do have sort of a setup of 3 things, start on the right, go to the left, and keep, again, the guy in the middle for the end. If we do that on the guy on the bottom here, left, oxygen is going to be -2 in this case. And that's usually a very good place to start with, especially if you have oxygen there. Again, there's 3 of them, so that gives us kind of like a -6 overall happening there for the oxygen side. Going to the far other side, we have sodium, which is group 1, which means it will be +1 in this case. And in this particular case, there is no overall charge, so we got -6 and +1. That means that the iodine here is going to take on a +5 oxidation state. So the sodium here would be +1, the iodide would be +5, and the oxygen here would be -2. Any questions on that one there? So again, we're so used to iodine group 7 -1, and that again is true in an ionic situation. This is not an ionic situation. Really between the iodate here, the IO3-, they're all sharing electrons, and that guy is a polyatomic ion. So again, the iodine here is taking on a +5 arrangement, rather than what we would see in a straight ionic compound, where it would take on a -1 sort of charge. Looking up at the top here, fluorine is always going to be -1, so that's a good place to start with. And since there are 7 of them and there's no overall charge here, that means that the iodine in this situation would actually be +7 to balance it out. So the iodine here would be +7. The fluorine would be -1 in terms of its oxidation state. So again, in those 2 situations, we have the same element iodide, one a +7, one a +5, again, because of the way it's sharing electrons and what it is sharing electrons to. In the case up on top, it is a little higher positive charge because fluorine is pretty electronegative, right? Which means it's going to really suck those electrons away from the iodine when they're sharing electrons, going to make it more and more sort of positive. So in that situation, that's why we kind of see the larger positive charge. Any questions on that there? Bottom here, we got some potassium dichromate. Once again, I'm going to start at the oxygen side, and that's going to be -2. There's 7 of them, which gives us like a -14 overall charge. Going to the other side, we have potassium, which is +1. And there are 2 of them, which gives us a +2 charge. Overall, it does need to equal 0. The difference here, though, is we actually have 2 chromiums. So in this case, each chromium is going to be +6, as we would need a +12 there to balance out everything to 0. And that means that the potassium would have an oxidation state of +1, chromium +6, again, not +12, and the oxygen here would be -2, once again, not -14. Any questions on how to assign oxidation states or numbers there? So it's really, really important you know how to do this, because frankly, it will help you when you look at something and understand what is being oxidized, what is being reduced by the difference in the oxidation states. And that is what you could use in our little number line here to decide, are you going this way or are you going sort of that way? And it will help you know, kind of figure out reduction and oxidation. Any questions on that there? Okay. So now that we talked about, you know, really a little bit about redox reactions and balancing them and oxidation reduction, oxidation numbers, now what we're going to talk about is more specific ways to classify redox reactions. So once again, the redox umbrella is the big sort of classification. More specifically, you could classify reactions in a couple of different ways. So here we'll look at the first type of more specific classification, which is a combination reaction. It is also sometimes referred to as a synthesis reaction. And that is basically when you take 2 things and it makes one thing, is a synthesis reaction or combination reaction. And that's what we see here. We take some aluminum, we take some bromine, and we make aluminum bromide. And that is 2 things that make one thing. So that's your classic combination synthesis reaction. This is also a redox reaction that is happening here. The aluminum is by itself. It is 0 in terms of its oxidation state. The bromine there, the Br2, is also how it comes. So it is 0 in terms of its oxidation state. And once again here, the aluminum will now take on a +3 charge, and the bromine will take on a -1 charge. In this case, basically a transfer of electrons, metal and non-metal happening. Here we see the aluminum once again going from 0 to +3, so it is being oxidized. And we see the bromine going from 0 to -1, and it is being reduced in this case. That would mean that the aluminum would be our reducing agent in this case, right? And this would be our oxidizing agent in this case, in this particular case. So you can more specifically call this reaction a synthesis or combination reaction. It is still really a redox reaction that's actually happening here, and it is a transfer of electrons in this case. Any questions on that there? The sort of opposite of a combination or synthesis reaction is a decomposition reaction. And the general form of that is you start with one thing and you make a couple of things. So you start with one thing, kind of break it apart. It's kind of the opposite of a synthesis reaction. Synthesis, you put it together, and decomposition, you basically break it apart. So that's what we see here. We see some potassium chlorate that makes some potassium chloride and a little bit of oxygen gas in this reaction. Once again, this looks like a decomposition reaction, but it is also a redox reaction happening. If we look at the oxidation states here of potassium chlorate, the oxygen is -2, the potassium is +1, and once again in this case that's going to give us -6 and +1, so the chlorine here is +5 in terms of its oxidation number. Going to the right-hand side, the chloride here is actually -1, and this is +1, as that is an ionic compound, so they have their normal sort of charges associated with it. And the oxygen actually ends up being 0 in this case. So this, once again, is a redox reaction. What is being oxidized in this case? Which element is being oxidized as you go from left to right? If you are not sure, let's take a look at it. Let's take a look at the oxygen to start with. Oxygen starts at -2, which would be here, and it ends up at 0 on the right-hand side. So it actually is the one being oxidized in this case, is the oxygen here. The chlorine started at +5 and ends at -1, which is actually going in that direction. And it is being reduced in this case. It is the chlorine that's being reduced. What is happening to potassium? Nothing. It's staying the same. So it's kind of like a spectator ion in a sense here. Nothing really happening with it. It's +1 on the left, +1 on the right, kind of like a spectator ion just kind of hanging out. So again, here you could use our oxidation numbers to figure out what is being oxidized, what is being reduced. And in this case, obviously, the chlorine is being reduced, which means that would be our oxidizing agent, the chlorine. And our oxygen is being reduced, being oxidized, which would be the reducing agent in this particular case. Any questions on that? So once again, big classification, redox reactions, more specific classification, combination or synthesis or decomposition reactions fall under that umbrella. Some other types of reactions that also fall under that umbrella are combustion reactions. And this type of definition of combustion is sort of a pretty generic definition. Pretty much, if you want a combustion reaction, that's all you need there, is you need some oxygen basically by itself there on the left-hand side, and you technically can classify it as a combustion reaction. For the most part, though, when people talk about combustion reactions, they oftentimes think about more of the organic combustion, where we talked about, like when we did the empirical formulas, you take an organic compound, you take some oxygen, you make a little CO2 and water. So that is sort of a classic organic combustion reaction, which is what a lot of people sort of think about when they talk about combustion reactions. But really the bare definition of combustion reaction is pretty much you just need oxygen present there on the left-hand side, and it's a combustion reaction. So these two here would be classified as combustion reactions. They also are redox reactions. This is sulfur, which by itself has no oxidation state or 0. Oxygen in its natural state will also be 0. When we come over here, the oxygen is carrying a -2 oxidation state, and that means that the sulfur here is actually carrying a +4 oxidation state. In this case, sulfur is going from 0 to +4, becoming more positive. So it is the sulfur here that is being oxidized. and it would obviously be our reducing agent. By default, by the way, once you figure out one, the other thing is going to be the opposite. There is going to be reduced and would be our oxidizing agent. And we see that by going from 0 to -2, so becoming more negative. If you follow it on the little chart there, it's being reduced. Over here, our magnesium, which is 0, and our oxygen, which is 0. Over here, it makes an ionic compound where the magnesium has a +2, oxygen has a -2. So once again here, magnesium becoming more positive, which we would expect in this situation, and it is being oxidized. And by default there, that guy would be reduced in this particular case as it goes from 0 to -2, becoming more negative. So the two reactions that we see here fall under the big umbrella of redox reactions. They also can be classified as combustion reactions, and actually both of those could also be classified as combination or synthesis reactions, as they are two things that make one thing. So as you can see, you can really classify the same reaction in multiple ways depending on sort of what you're looking at. So both of these reactions could have really three different types of classifications, could fall under redox, could be a combustion reaction, and could be a synthesis or combination reaction that's happening here. Any questions on that there? So that's something that happens a lot. You can really classify the same reaction multiple ways depending on sort of what you're looking at. Another really important type of reaction is a single replacement reaction, and a single replacement reaction is a redox reaction that takes place, and there's really kind of a couple of different ways, but we basically have one thing coming in, for example, and kicking out something else, as we talked about, I think, in a couple of earlier experiments. In order for that to happen, whatever is coming in needs to be more reactive than what it's replacing. So whatever is sort of coming in, it needs to be more reactive than what it's replacing. If it is not, then it will not happen. You will not get a reaction that will take place. We saw it with those halogen ones we did with the different layers and things going from one layer to the next. Those were all sort of single replacement reactions. The way you can recognize them different than a double displacement reaction is typically you only have one ionic compound and you have something kind of by itself in this sort of natural state. So maybe a metal, maybe a halogen or something like that. So for example, in this is a hydrogen displacement. The metals coming in is kicking out the hydrogen. And on the other side there, we get H2 that comes out when hydrogen comes out by itself. We look at this one here. It is a metal displacement. The magnesium's coming in and kicking out the Ti. When it does, the guy that gets kicked out comes out by itself in its natural state, uncombined. And here's a halogen replacement like what we saw in that experiment. The chlorine is going to actually come in and kick out this guy. We could think of water sometimes as H and OH, kind of like a positive negative thing here. So again, when the strontium comes in, it kicks out the positive hydrogen, which is why it comes out as H2 on the other side. Again here, positive, negative. Magnesium doesn't have an oxidation state here, but when it does, it is positive, so it will kick out the positive guy. And chlorine doesn't have an oxidation state here on the bottom, but when it does, it will be negative, so it kicks out the negative guy. So the guy coming in will kick out whichever one has a similar charge to what it normally would have. So if it normally would have a negative charge, it will come in and kick out the negative guy. If it normally has a positive charge, it will come in and kick out the positive guy. All these guys can be even more specifically classified as hydrogen displacement, metal displacement, or halogen displacement, are more of a broad classification of single replacement is also what is sometimes referred to. Every one of these guys are also redox reactions that are occurring. In the case over here, the strontium is 0, the hydrogen is +1 and -2. On the right-hand side here, the strontium is +2. And then we have our -2 and +1 and 0 happening here. So we have our strontium going from 0 to +2, so being oxidized. Our hydrogen going from +1 to 0, being reduced here. Same thing here. This is +4, -1, 0, 0, +2, and -1. So once again here, the titanium there going from +4 to 0, so it's being reduced. Magnesium going from 0 to +2, being oxidized, becoming more positive. And lastly here, 0, +1, -1, +1, -1, and 0. Chlorine going from 0 to -1, becoming more negative, so reduce. The bromine here going from -1 to 0, becoming more positive, being oxidized. And once again here, the potassium just kind of hanging out, nothing really happening with the potassium on both sides, has the same oxidation state. So all three of these guys are single replacement reactions. Again, you can be really more specific about it as hydrogen displacement, metal displacement, or halogen displacement, but they all still fall under the big redox umbrella because they're all still oxidation and reduction reactions basically occurring. Any questions on any of that there? So how do we know if some reactions take place and some ones do not take place? There's a table you can sometimes look at and sometimes referred to as an activity series. And the basic aspect of it is, you kind of have the guys on the right here. And pretty much anything that is higher up on the table is more reactive than anybody lower on the table. So that replacement will occur. And typically anything lower on the table is less reactive than anything higher on the table, so it will not replace it. Sometimes though, in certain cases, you do need a little bit more there to get some hydrogen displacements to occur. For example, here, if we take calcium and water, we can find calcium up on the table and it will react with cold water to produce H2. So that's all it needs. But if you take something like lead, for example, you actually need something a little bit stronger like a acid to get that reaction to take place. And in this case, with water, it would not actually take place. So that's how you could sort of figure that out. This one we actually did together in the lab there. And the activity series for the halogens is basically group 7. And as we saw, right, in group 7 on the periodic table there, reactivity increases, right, as you go up. So we saw that bromine would replace iodide, right? And chlorine would replace bromine, but iodide would not replace chlorine again. So you could use group 7 on the periodic table as sort of an activity series for the halogens. Again, anybody higher in group 7 will replace somebody lower. Anybody lower in group 7 will not replace anybody higher. And that's what we see here. We see chlorine, which is higher in group 7 than bromine. So we would expect that displacement to occur. But when we look at iodide, it is actually lower than bromine on group 7. So that displacement would not happen here when we look at the halogens. Any questions on that there? Now, one last type of sort of oxidation reaction that sometimes occurs is what's sometimes referred to as a disproportionation reaction. And that's a really fancy way of saying the exact same element in that reaction gets both oxidized and reduced at the same time. So it is possible for the exact same element on the left to go through both things, being oxidized and being reduced at the exact same time. And that's what we see here. So if we just kind of run through our chlorine, which is really what's happening here, oxidation state of chlorine there on the left is 0. We have -2 and +1 for our hydrogen. Over here, the oxygen is -2, and that means that the chlorine here, because there's a -1, would be a +1 in that situation. This is chloride, which means that it has a -1 oxidation state, and then that's -2 and +1. So what we have happening here is the chlorine on the left is going to basically ClO-, where this guy is +1 and 0. So it actually is becoming more positive here. So this is going through oxidation. We'll give off an electron. Then the chlorine is going to chloride, 0 and -1, becoming more negative, which means it will gain a couple of electrons here. And we'll have our reduction reaction that's happening. So in this particular case, the chlorine, the Cl2, is actually going through both processes. Occurs a lot. There's chlorine chemistry up in the atmosphere. It happens a lot. And we do get these sort of same element being both oxidized and reduced. How you would write your half reactions is just what I did there. You would start with the same guy on the left for both and what it forms there on the right. Any questions on that there? Okay, so once again, two big classifications of reactions: double displacement, where we have acid-base reactions, and precipitation reactions. Redox reactions is the big umbrella where you have synthesis, combination, decomposition, single replacement, and combustion all fall under those sort of big umbrellas of types of reactions. So here we could go through and classify some of these reactions. First one is a precipitation reaction, as calcium carbonate would be a solid. That's an acid-base reaction. H plus is an acid, NH3 is a weak base. That's a single replacement reaction, which is a redox reaction, the zinc coming in and getting out the hydrogen. And this is also a redox reaction or a combination or synthesis reaction. Again, basically electrons being transferred in this case. Any questions on how to classify reactions? So again, double displacement, precipitation, acid base, and redox, pretty much everybody else. So combination, synthesis, decomposition, single replacement, and combustion. Any questions on any of that there? Okay, we will talk a little bit more about redox probably tomorrow, a little bit how to balance a little bit more difficult ones, which will help you with study assignment coming up, I think, in the next day or two. But for that, I think that should wrap this, if I'm not mistaken. It does. All right, give me a second. We will continue on. Okay, next thing we're going to talk about is stoichiometry. We're also going to talk about molarity and concentration, and we'll also talk about titration as well. So it comes from a little bit of a bunch of sections from different chapters, I believe. So the first thing we're going to talk about is stoichiometry. And stoichiometry is calculations that we use, really combining two things that we've talked about, balanced equations and basically grams to moles is a very big thing that we use. And there really is sort of 4 basic steps to stoichiometry problems. And the 4 basic steps to follow when you're doing pretty much basic stoichiometry problems is you always want to make sure that you write a balanced equation. Pretty much nothing works correctly in stoichiometry if you do not have a balanced equation. And that is because when we use stoichiometry or the equation, let's say we had a little H2 plus some N2, 2 there and a 3 there. When we have a balanced equation such as this, we can really write relationships that we could get from the equation. And we saw it, I think, in another chapter. But the one that we will focus in on, obviously, with stoichiometry is what is referred to as the mole-to-mole relationship. And the mole-to-mole relationship really comes from the balanced equation. And it comes, frankly, straight from the coefficients. And the coefficients in the balanced equations are referred to as the moles of each of those guys. So for example, here we could say from this equation that there are 3 moles of hydrogen react with 1 mole of nitrogen. We could also say for every 3 moles of hydrogen we throw in there, we get out 2 moles of NH3. For every 1 mole of nitrogen we toss in there, we get out 2 moles of NH3. So these 3 equalities are what are sometimes referred to as stoichiometrically equal to each other, and they are not equal to each other, obviously, in terms of numbers. So obviously 3 does not equal 1, but they are equal to each other in terms of like proportion that you need to throw into that reaction to produce a certain amount of product. So kind of like when you make cookies or whatever it may be, you got to put so much flour, so much sugar, and all that kind of stuff in there to make a dozen cookies. Same thing here. In order to get this reaction to occur, you need to throw in 3 times the amount of hydrogen to nitrogen to produce that NH3. Because these are really equalities, it's really like basic equalities and stuff that we talked about in an earlier sort of chapter. You basically could write conversion factors for each of these things. So for each of these equalities that we see, you could write 2 conversion factors. For the first one, you could write 3 moles of H2 over 1 mole of N2, or 1 mole of N2 over 3 moles of H2. For the second one there, you could write 3 moles of H2 over 2 moles of NH3 are 2 moles of NH3 over 3 moles, there we go, 3 moles of H2. And lastly, for the bottom one there, you could do 1 mole of N2 over 2 moles of NH3 are 2 moles of NH3 over 1 mole of N2. So from this one equation, one balanced equation, we basically have 6 different conversion factors that we could use in a problem. Would we need to use all of them in a problem? We would not. We would just use obviously whichever one, you know, we needed. And we could do basically dimensional analysis and convert it. So what is stoichiometry? Frankly, stoichiometry is really just a conversion factor. The difference is where you get the conversion factor. So instead of looking it up in a table, you use the balanced equation basically to pull your conversion factors from. And that's because in a typical stoichiometry problems, they will give you information about things you're really not interested in, but you're interested in somebody else in the equation. So you need a way to go from like a reactant to a product, or a product to a reactant, one reactant to the other reactant, or one product to the other product. So you need a way to kind of convert from one of those things to the other. And this is basically, you know, what we use to do that. Any questions on that there? So that's why number 1 is really, really important. If you are not using a balanced equation when you're doing a stoichiometry problem, frankly, you're just messed up from the beginning. Nothing's going to come out right, so it does need to be balanced. The next thing that you want to do is convert whatever they give you, whatever units it may be, you need to convert them into moles. So very commonly, this implies that we usually go from grams a lot of times to moles, but it definitely can be some other unit. And a reminder that it is the molar mass from the periodic table that allows us to do that conversion. That is grams per mole that we could get. So a lot of times we do at some point need to use the molar mass from the periodic table to convert from grams to moles. But you could be given something like in, you know, pounds. So you might have to go from like pounds to grams to moles. So there could be a multiple types of conversions that you have to do. But ultimately, the last part is to go from grams to moles usually. And really the reason for that is what the big stoichiometry thing is about. It's about these mole to mole relationships that we could get from the equation. So we got to get everybody into moles so all the units cancel out correctly so that we can pick the right mole to mole relationship that we could get from the equation. And that really is the third part, which is the big stoichiometry part. Is simply like the mole to mole sort of calculation. And that allows you to go from one thing in the equation to the other. Now, do you always have to go across the arrow one way or the other? You don't. You could do the relationship between 2 reactants. You could do the relationship between 2 products. You could go from reactants to products, products to reactants. So you could go anywhere you want in that equation. Once you do that, you will typically, you should always be at this point in units of moles. And a lot of times you don't really want moles as your final unit. So you usually have to do some type of conversion, which is the 4th step, which is go from moles to some other unit. A lot of times, once again, it could be grams. So you may use, again, the molar mass here on the back end to do that. Or it may be some other unit that it may want. So maybe 1 or more sort of conversions along the way. These are the 4 basic steps for a stoichiometry problem: balanced equation, convert to moles, mole to mole relationship, and convert those moles to some other unit. Any questions on that there? So for example, here, you know, if we had, say, let's say we produced 25 grams of NH3, how many grams of H2 did we start with? Right. So if we were to do this here, we will do our basic 4 steps. Step number 1 is to have a balanced equation, which we do up here. So obviously that is good to do. Step number 2 is to take whatever they gave us and convert to moles. So step number 2 here is they did give us grams of NH3, so we would need to convert that into moles. NH3, we would need to get the molar mass to do that. So from the periodic table, nitrogen is 1401, and there are 3 hydrogens at 1.008. Gives us a 1703 is the molar mass of NH3. So step 2, we would take our 25 grams of NH3. We would use our molar mass here from the periodic table. We would want grams on the bottom so they cancel. 1703 grams per mole of NH3. And if we got an answer at this point, it would be, we'll call it something like 1.468 moles of NH3. So that is a very basic second step that you do a lot, is to convert grams to moles. The problem though is at this point, we are stuck, if we think about it, over here at NH3. And we're not really interested in NH3 in this case. We're interested in how much H2. So we want to get over here. And that is really where the third step in the stoichiometry part comes from it. So we would go to the equation. We would find our relationship, which is this one right here. That would give us our 2 conversion factors that we can use, either this one or this one. In this particular case, we have NH3, but we want H2. So the conversion factor that we would want to use is the one where NH3 would cancel out. So we would want to use this conversion factor here to do that. As again, you just take it like a dimensional analysis type problem, cancel out the units. So if we do that, we would take our number that we had above, 1.468 moles of NH3. And this is going to be the big stoichiometry step here. We want to get rid of NH3. So we would have 2 moles of NH3 on the bottom and 3 moles of H2 up on top. And that is the stoichiometry part right there. That allows those 2 guys to cancel out, step number 3. And if we did that in this particular example, we would end up with not that number, 1.468 times a 3, a little dividing by 2, gets us 2.202 moles of H2. So in this case, we just did stoichiometry to go from NH3, which is what we're not interested in, to H2, which is what we are interested in. And if we happen to want to know how many moles that was, this would be the answer. This would be technically what is sometimes this would basically be what we are starting with in this particular case. But we do want grams, which means we do need to do step number 4, which is one last conversion, which is basically to take it from moles to grams. But we do have to remember in this case, we are now at H2, so we want the molar mass of H2, and we do not want to use, obviously, the molar mass of NH3 at this point. So if you go to the periodic table, you would see that there are 2.016 grams per mole of H2. Again, from the periodic table to do that, that is going to cancel out the moles and give us 2.202 approximately. We'll go with 4.4 grams of H2. So all basic stoichiometry problems pretty much are these 4 steps, and you just kind of go in that order. If something is done for you, you do not want to undo it. I've seen people do it for some weird reason. So for example, if your numbers are given to you in moles, you don't need to unconvert it to grams and go back to moles. So you just continue on, obviously, with the process here. So really what this number represents is, if I want to produce, in this case, 25 grams of NH3, I would need to toss in there about 4.4 grams of H2, and I should produce, if everything went perfect, ideally 25 grams of NH3. So once again, the relationship in terms of stoichiometry allows you to, again, go across the arrow from left to right, right to left, stay on the left-hand side of the arrow, stay on the right-hand side of the arrow. You could use stoichiometry, obviously, between 2 reactants, 2 products, reactants, and products. Any questions on any of those steps there? All right, so why don't you try one here? Methanol burns in air according to this equation if you had 209 grams of methanol, which would be this guy here. Are Or use up what is the mass? So how many grams of water would we produce here? We're going to give you some numbers that might be helpful. Carbon is 12.01 on the periodic table. Oxygen is 16. Hydrogen there is 1.008. All right, take a few minutes. We want to know how many grams of water would we produce in this case. So this is a basic stoichiometry problem. The reason it's a basic stoichiometry problem is pretty much you're just given one piece of information. So in this case, we have information about a reactant, and that's how you know sort of a basic stoichiometry problem. So we'll follow our steps. Step number one here looks like it's done for us, so that's good. We have our equation that's balanced. Really, step number two here, we want to convert to grams to moles, and we do need to do that in this case. Once again, here we would need the molar mass of methanol, which looks like 12.01 plus we got 4 hydrogens there, 1.008. And we got an oxygen, which is 16 grams per mole. And that's going to give us looks like 3204 grams per mole would be our molar mass. So step number two, we'll take the grams that was given to us, 209 grams of CH3OH, using the molar mass from the periodic table. We will get rid of that there. There we go. We'll put the grams on the bottom so that they cancel. It gives us 3204 grams per mole of CH3OH. Gets us 209. If we get an answer at this point, 3204 gives me something like 6.5231 moles of CH3OH. At this point, step number three is to go to the balanced equation and find the two things we're interested in. In this particular case, one thing we're interested in is obviously what they gave us, which would be this guy. The second thing we're interested in is obviously what we are trying to find, which is water in this case, which is that guy right there. So from the equation, we could find our mole to mole relationship, and it is basically 2 moles of CH3OH gives us 4 moles of water. And once again, we could use that to write 2 conversion factors. In this case, we will continue on 6.5231 moles of CH3OH. I want to get rid of the methanol, so I'm going to put that on the bottom so it cancels. Remember, opposites cancel. Up on top is what I want, which is my water. The moles of the methanol cancel, and we end up with, at this point, looks like maybe 13.046 moles of water. At this point, this is how many moles of water we would have produced, also sometimes referred to as the theoretical yield, but we don't want moles at this point. We actually want grams. So we do have step number 4, which is we need the molar mass now of water to do that, which would be 2 times 1.008 plus a 16 there. Gives us 18.02 grams per mole as the molar mass of water. We're going to use as a conversion factor here, 13.046 moles of water. Using our molar mass, where grams in this case would go up on top, so we end up with grams. The moles of the water cancel, and we end up with about 235 grams of water would be produced. And once again, this is sometimes referred to as the theoretical yield. Basically how much we produced in this case of our product, if everything went perfectly in this particular case. Any questions on those 4 steps? You absolutely could do them all together or just one big calculation. It's all good. I just did it here, obviously, to break it apart. If you do break it apart, which is perfectly fine to do as well, just, try not to round too much to the end again, so you kind of get to the end. Any questions on any of those there? All right, why don't we try one more here? Why don't we do the do the same equation there. So CH3O2. So let's say, actually, let's do this. Let's say we produce, what do we got there? Exactly what we just did there, 235 grams of water. How much CO2 in grams would be produced? All right, take a second and calculate that. I will as well, because I just made it up. Okay, let's take a look. So in this case, we produced our water that we just calculated, and we're actually interested in how much CO2 we would get with. Well, again, it's a basic stoichiometry problem. Pretty much just have one piece of information given to us, which is the 235 grams of water. So we'll follow our 4 steps. Step 1 already still done for us, which is to balance the equation. Step 2, we do need to convert to moles. So we'll take our 235 grams of water. We calculated the molar mass of water in the previous problem, which was 1802 grams per mole. Once again, the grams would cancel out at this point. We'll take 235 divided by 18.02, gets us about a 13.0411 moles of water. At this point, we're not really interested in water, but we're interested in CO2, so that is where the stoichiometry part comes from. From the equation, we see 4 moles of water will also produce 2 moles of CO2. So we're going to use that as our conversion factor to go from water to CO2. So doing that, carrying on with our number here. In this case, we want to get rid of water, so we do want to put water on the bottom. So that would be the 4 moles of water up on the bottom, or down on bottom. Up on top there would be our CO2, and that is the big stoichiometry part right there. So we're going to take this times it by 2 divided by 4, going to give us a 6.5205 moles of CO2. Any questions so far? At this point, once again, we're interested in grams, so we do need to do step number 4, which is to take those moles and convert them into grams. So 6.5205 moles of CO2. We do need the molar mass of CO2, so that is 12.01 plus 2 times 16, like a 4401 there for the molar mass. We're going to put the grams up on top, 4401 grams of CO2 per mole. Again, we cancel out here and times it by 4401, 6.5. Looks like 287, we'll call it, grams of CO2 would be produced in this case. First off, any questions on any of those steps? Again, same 4 steps. Once again, you could do it all in one calculation if you like. The other thing is really important, as we talked about previously, molar masses, just based on the formula, not the coefficient that's in front of there. So that's a very common error people make, especially in stoichiometry problems. Any questions on basic stoichiometry problems? Okay, so there are other stoichiometry problems, which are referred to as limiting reagent problems. So limiting reagent problems or limiting reactant problems, in most sort of calculations or reactions to take place, there's always some reagent that gets used up first. And that is what is referred to as the limiting reagent. So the limiting reagent always gets used up first. And that also leaves a reagent where pretty much you have plenty of, and that is what is referred to as the excess reagent. You have plenty. Is still there at the end. So in this example here, the NO is the limiting reagent. I believe it is the blue and red circles. And the excess reagent is the O2, which is just the red circles. And you can see at the end there, we have just some red circles sort of left over, and that is the excess amount. So in limiting reagent problems, you're oftentimes asked, how much product you would produce. You also are sometimes asked how much of the excess reagent is left over at the end of the reaction. Why limiting reagents are important is very simply, if you take A plus B to make A and B, and let's just say that A was our limiting reagent and this guy was our excess reagent, it is the limiting reagent which is always responsible for how much product you will produce. And that is because in this very simplified example, in order to make the product, you need an A and a B. So if A runs out, there's no way to make any more product at that point. So the limiting reagent always determines how much product that you are going to make. And that's why in limiting reagent problem, you need to at some point figure out which one is the limiting reagent, so you can figure out how much product that you can make. The way you could calculate this is similar to what you could do in a basic stoichiometry problem. There's actually many different ways to sort of calculate it. I'm going to show you maybe a different way than maybe if you've seen it before, a little bit different way of doing it. But it's always important to determine the limiting reagent when you're doing these type of problems. How do you know it's a limiting reagent problem? You know it's a limiting reagent problem because, frankly, they give you enough information for the reactants to get to moles. So whatever they give you enough information for both reactants to get to moles. That's definitely how you know it's a limiting reagent problem. If you're just given enough information about one of them, it's a regular basic stoichiometry problem. But if you have enough information about the two reactants that are there in most cases to get to moles, it's definitely a limiting reagent problem. So you have to take that step to figure it out. Any questions on that there? Okay. So we're going to go through this problem here. I think what we will do is we will do it at the start of lab, so that will help us. So we'll go through it in lab and talk about it, so we're not rushing here through it at the last little bit. All right, so we will lay it up there for just a second.